the internet for other people who are unable to attend to watch. So hello and welcome. Today I'm going to take you through an introduction to ecological forecasting. Just an overview of what we'll be doing today. I'll be introducing some of the concepts of ecological forecasting, some of their different applications, and walking you through the iterative forecasting cycle. Following this, we'll go out into breakout rooms and we'll be using our Shiny app, which we have developed to work through two different activities. We're going to focus more on activity A and activity B, followed by people coming back together and discussion at the end. So in activity A, you'll be getting data from an ecological site and building a very simple ecological model. And then in activity B, you will step through each of the different stages of the forecasting cycle and use these to generate an ecological forecast. And activity C is kind of what we'll do at the end, where we will reconvene in the main room and talk through the different results that people have from their different sites. But before I get kind of started, I just want to give you a quick overview of the project EDDIE. So EDDIE stands for Environmental Data-Driven Inquiry and Exploration. It is, or inquiry, depending on how you say that word. But yes, so you can see the website at projecteddie.org, where there is a suite of different teaching modules which are prepared, which allows kind of instructors to download these materials and then apply them or use them in their own classrooms. So within Project EDDIE, we have Macrosystems EDDIE, which is led here at Virginia Tech, where it's kind of looking to teach local to continental scale ecology. And it's about getting students to kind of develop and test hypotheses, introduce them to ecosystem modeling, learn basic R programming, and using Shiny apps to kind of tap into that ecological forecasting side of things. So for today, back to this, yeah, Professor Kaylin Carey is here with me, and also Dr. Ryan McClure is going to be my teaching assistant, so you can see them here, and they'll be kind of helping work through the different activities that we have today. So just to set the scene overall, ecosystems worldwide are changing, and this is in the context of climate change and land use changes. And as a result of this, we are seeing different pressures across aquatic and terrestrial ecosystems. For today, we're going to kind of focus in on lake and aquatic ecosystems, because we know that these are key providers of ecological services, and being able to understand how they will change in the short term is critical to help management of these resources. And I just want to say, if people have questions throughout, either drop them into the chat or unmute, and feel free to interrupt throughout. So before we start, would anyone like to say, what is a forecast? So either in the chat or you can unmute yourself, anyone. When you hear forecast, what do you think?
I'll go. I think about short-term predictions of future conditions, usually weather.
Usually weather, yeah. Yeah, prediction based on previous data, prediction of future conditions. Yeah. So the definition that we're going to be kind of working with is, yeah, it's a prediction of future events with uncertainty. And I'm going to kind of dive into this uncertainty a little bit later, but just to kind of frame the idea of forecast, like I said, future events. So some of the things that kind of underpin this is they are events that haven't yet occurred, and it also gives a probability likelihood of the event to occur, and then they're actionable in terms of whether or not you can actually do something to influence an outcome. So can you think of some examples of things that we do forecast? Anyone want to throw some suggestions? Weather, which is, yeah, water quality, purple ones, climate, COVID-19, algal blooms, stocks, yeah. So yeah, as you can see, there's many different things that we forecast, and here's just even just in a abridged version of this. So things from weather through to extreme events such as floods, hurricanes, or forest fires, and then things like economy and disease transmission, which we all kind of become too familiar with in the last year and a half. Election results are always put into forecast greenhouse gas emissions when they try and do climate change scenarios and things like that. Earthquake prediction, land use, player and team performance, and yeah, much more. So going back to that, then we can forecast and we want to predict how they will change into the future. What is the main purpose of a forecast? What do you use a forecast for when you get a forecast? To make decisions, avoid future problems, planning, management, take action, prepare. Yeah. So there, the two kind of things we have is preparation. So for the example I'm going to use is this for weather forecast and for hurricanes, that it allows, having a forecast allows people to prepare and anticipate what is going to occur. But then there's also actions, actions that can be taken. So in terms of disease forecasting or fire forecast, steps can be taken to, or actions can be taken to prevent or reduce potential future outcomes. So the kind of key difference here is that a hurricane, there's not much you can do to stop a hurricane. Although I did hear people trying to detonate an atomic bomb in the eye of a hurricane, but apparently that's not advised. But apart from that, we can't really do anything, but we can take action to prepare and to work with that information about the forecast to prepare for the future. So our focal question today is kind of taking some of this and trying to dive into what defines an ecological forecast. And how we are going to frame that today is in terms of similar to like the forecast, but a prediction of future environmental conditions with uncertainty. And you'll kind of see that this idea of uncertainty is reoccurring because this is crucial when it comes to forecasting. And the reason is this is because forecasts are a well-informed guess of the future, and it will always be uncertain. And we use uncertainty in different ways, and it influences how we make decisions and how we evaluate risk. And generally, like further on to the future we go, the uncertainty generally increases. And here is just a plot showing kind of prediction of or forecast of air pressure going 16 days out into the future. And you can kind of see that like today, tomorrow, we have a generally good idea of how it will turn, but then as we get further into the future, the uncertainty bands grow. So now I'm going to step through the different stages in the forecast cycle itself. And then I'm going to break them down and go into a bit more detail after. So first of all, it starts with creating a hypothesis about how your environmental variable responds to different covariates. Then you will build a model to explain this hypothesis. You will look at quantifying different sources of uncertainty. You will then generate your forecast. Following that, a key part is to communicate a forecast, because as we kind of mentioned earlier, it's like if a forecast is if you're gonna use it to take action or to prepare for something, it needs to be communicated effectively. Once you go into the future, you can collect more data, and as soon as you have new data, you can then assess your forecast. And then from assessing your forecast, you can tell how well your model is predicting the future. So then if it's not doing so well, you can then update your model and then step back into the cycle in terms of quantifying uncertainty and generating the next forecast. So I'm going to step through each of these now just in a little bit more detail. But the important thing to remember is that this is an iterative cycle, which means that it is a repetitive cycle and it is done over and over again. So the first step, which is to create a hypothesis. So a hypothesis is an idea that proposes an explanation about an observed phenomenon in the natural world. And the kind of example that we're going to use is like when there's an increase in light, there is an increase in algal biomass in the lake, because this is the kind of example that we'll be using throughout today. So this is our hypothesis. And then we can go out to the field, collect data, but then we can use this to inform how we expect this to react. So we can build a model and you can use a mathematical model. So we can say that the amount of phytoplankton today is equal to the amount of phytoplankton yesterday plus a rate of or increase in reproduction as a result of nutrient uptake minus mortality as phytoplankton die. And then that will give us the amount of phytoplankton that we have today. So this is a very simple model. So then we can quantify the uncertainty. So this is about characterizing and trying to reduce the uncertainties in the forecast. So for example, we don't know what the future weather is going to be in the next week to 2 weeks. So we can use weather forecast data. And using this is a way of being able to quantify the potential differences among different scenarios and this, how it contributes to our forecast uncertainty. And here is a plot down here showing a 10-day forecast of air temperature. And this is showing 15 members of an ensemble. And you can see how the further on into the future, the spread of the ensembles increases. The next step is to generate a forecast into the future. And this is, you'll be using the model, and then your key part of what makes forecast a forecast is that it's being driven by forecasted driver data. So for example, you're doing this, you're forcing your model with forecasted water temperature and forecasted incoming light. And this is a plot showing, again, I think it's 30 members of a forecast of primary productivity within a lake. The next step then is communicating a forecast to stakeholders. And this can be done in a variety of different ways. And we have another module that we've developed as part of this series that kind of dives into this aspect about how communication and visualizations can be used to improve management. But how we create the visualizations of the data is important when we think of kind of in terms of end users and stakeholders and who is going to be using this forecast and how they will use the visualization to interpret what's going to occur. So this is a plot showing what was shown on this previous slide, but doing it in terms of giving a 95% confidence interval of the forecast, and the solid line represents the median. So then the next step is to assess the forecast. So as time moves forward and 1 week into the future, we can collect more data. And as we have more data, we can use this to compare to our model. And then we can see how well it performed. And this can be done using statistical or visual measures. And this can give you an idea of whether or not, okay, is my model performing well? Is it actually predicting it? And then if it isn't, or if it is, you can then look at potentially updating your model. So this would involve either you can be updating model parameters or rewriting a model, adding a new covariator, things like that. But these are some things that you can do to improve, update your model. So that's kind of all of the steps within the forecast cycle. Does anybody have any questions regarding anything? Any of the aspects there?
There's a question in the chat from Ulrike.
Okay, and that's it. Yeah. Mm-hmm. Yeah, that's a good question, because it's something that isn't kind of counterintuitive, but it's trying to identify and quantify the uncertainty before the forecast, because this is what contributes to the uncertainty in the forecast when you generate the forecast. So it is that step a bit earlier.
Does my response answer your question, Ulrike?
Yes, it does, but now I have another one. And I was thinking that this is similar to do some type of training a model and then testing a model. I mean, you could also do split the period in a known period where you train the model, and then for testing the accuracy, you take the test part. I was thinking this is quite similar to regression, to random forest, for example, how you do it. Was this clear?
Yeah.
So
no, that's and that's kind of in principle to a degree what it is, what it's doing in terms of. Okay, I think, sorry, my battery is a bit low. on my computer. Oh no, it's okay. I think I should be fine for the next while. Sorry, but yeah, exactly. That as you move forward in your forecasting, that you are kind of through the process of data assimilation and doing that comparison, that you can update your model state. So it's not the exact same methodology of using a random forest or regression to train your model, but it is similar in principle.
And I think the beauty of the forecasting cycle is that you can use machine learning methods like random forest, or you could use process-based models. You know, it doesn't, you can apply kind of the same conceptual framework to whatever your modeling platform is.
Okay, thank you.
Does anybody else have any other questions?
Maybe one to clarify. For ecological forecasting, do we always need drivers forecasted drivers? This is like an assumption that we always need. For example, for lake water quality, will we always need forecasted weather data?
It is, yeah, that's a good question. Because that's one that we often struggle with in terms of trying to like accessing the forecasted data if you're trying to predict something on a different time scale where there isn't data available. Yeah, so there's different ways in which that can be approached. But it would come down to how you would build your model, because you would need to use a model that is using a covariate that can be predicted to some degree, even if it's, so if you're doing a simple like a growing degree day model for like a terrestrial ecosystem, that like, you know, using the growing degree day or even like day of year can be like a little, or can be one of those kind of covariates that you can kind of predict. So, but yeah, it is kind of crucial that the model has some degree of covariate that is forecastable.
I think there's a lot of kind of discrepancies in the literature as to what's defined as an official forecast or not, but using our you know, kind of definition of the expectation of trying to make future predictions, it has to have forecasted drivers to be considered a true forecast.
Thanks.
Okay, so today what we are going to do is we are going to use a model to generate a forecast of primary productivity in lakes, and we're going to be using real data from lake sites. Just to kind of give you an overview, is that the model itself is a representation of phenomena, when using this to kind of understand and use this to hopefully predict what's going to happen. And we're going to be working on predicting chlorophyll A concentrations in a lake. So what are the kind of the key main drivers? And so just to clarify, this education material is for ecological students. So I kind of feel like explaining this to people from Glion is maybe a bit much, but just I can go through this relatively quickly. So as most of us I'm sure know, the main drivers of primary productivity of a lake are light, water temperature, the availability of nutrients, the phytoplankton biomass, zooplankton, and how all these factors interact to control primary productivity. And you'll, in the Shiny app that you'll be using, you'll be able to kind of interact with different factors to kind of control some of these drivers. So the primary productivity model that we'll be using is a very simple producer-consumer nutrient model. So an example in terms of a terrestrial model would be the producer being plants, the consumer being deer, and then nutrients being phosphorus, nitrogen, and how this cycle and energy from the sun. But we're going to be using a simple aquatic model. So this is an NPZ model, where zooplankton are the consumer that consume phytoplankton, and then the mortality of zooplankton and allows for the availability of nutrients, and then this gets uptaken by phytoplankton using in the presence of sunlight. But we're going to actually simplify this model a bit further. Just sorry for all the zooplankton ecologists out there, but we're just going to focus in on the phytoplankton and the and the nutrients, and looking at that relationship in the presence of light and then also water temperature. And this is our simplified model in terms of what how we will be predicting primary productivity in the lake. So the data for today that we will be using comes from the National Ecological Observatory Network. These are, yes, NEON is a continental scale observatory, and it's got sites all across the United States in different eco-climatic domains, and it's a long-term open access ecological data set that is designed to better understand how terrestrial and aquatic ecosystems are changing into the future. So here are the learning objectives of today's module, that by the end of today, you'll be able to describe an ecological forecast and the iterative cycle, to be able to explore and visualize the NEON data, to be able to construct an ecological model and generate forecasts of ecosystem primary productivity with uncertainty, be able to adjust model parameters and inputs to study how they affect forecast performance relative to observations. And then we're going to, at the end, do a comparison between the different sites that people will have generated forecasts for, and kind of discuss some of the similarities and differences between the different sites. So now I'll give you a quick overview of each of the activities. So in activity A, this says work in pairs, but we're going to be going into breakout rooms of about four people per breakout room. And what you'll do is you'll select a NEON site. You'll kind of explore some of the data coming in from this site, and then you'll build an ecosystem model and kind of calibrate it to your site. Yeah, so I have it here in pairs, but you're working in fours. So for activity B, you will be stepping through each of these steps in the cycle, which includes quantifying uncertainty, generating a forecast, communicating a forecast, assessing a forecast, updating your model, and then generating the next forecast. And then activity C, where what we're going to do actually is we're going to come back together and kind of discuss and talk through the results from the different sites that people have generated forecasts for. So just to give a bit of background, so today's app has been developed using the R platform, our Shiny platform. So what this does is it takes R code and it builds an interactive web page, and it allows you to have interactive plots and allows you to visualize and explore data and kind of answer questions within the app itself. And just last shout out for anyone here is interested in teaching, just as you go through this, if you find that this is something that you really like, or you could see yourself teaching in your own classroom, we are currently recruiting testers to use these educational materials in their classrooms in the next semester. So if you're interested, feel free to contact us, and I'll share this again at the end. So I'm just going to, we're going to go into log on to this, the Shiny app, and we're going to work in groups of 4. And just when you go into your breakout rooms, just as an icebreaker, it'd be good if everyone could introduce themselves. So just give your name, where you're from, and your favorite fruit, because fruit is good for you. Okay, so yeah, the link has been dropped in. So the thing just that we're going to work on first is oops. Okay. My PowerPoint has just stopped responding, which is okay, because I'm not doing anything important at the moment. So you're going to log on to this app, and if everyone could do this before we go out into the break rooms, it'd be really useful, because we're going to have I think like 30 people hitting this server at the exact same time. So sometimes it just takes it a while for everyone to log on, and as you can see, it's taking a while for mine to load. But while this is loading, does anyone have any questions or any comments on anything from the presentation?
Yes, I did not understand. Do we have to access from our PC the website?
Yes. Sorry, yeah.
And we should this do right now?
Yeah.
Aha. And this, what I see on the screen, is this the link?
Yes, it's in the chat as well. The Macrosystems EDDIE.
Okay, this I didn't see. Okay, thank you very much.
No problem. Okay, so mine has loaded. So this is what you'll see, and you'll see that there are tabs along the top of the screen where you can navigate through different aspects of the app itself. So I'm going to let you explore this, but I'm just going to show you some of the key features before I set you loose. So you can access, there's some of the key slides from the presentation are hosted here if you need to do a refresh, sure. But throughout the app, there are questions and activities that you need to complete. And so you'll see these green boxes with text boxes where you can fill out your name, ID number, but then there are these questions that you will be filling out into these text boxes as a way to kind of get you thinking about how ecological forecasts. And then as you navigate down, you'll see that there's this button, it's download user input. Because there's so many people accessing the server, sometimes it will crash. So I recommend that every time you get to the bottom of the page to like download this file, the file that it downloads is very small, but it just basically takes a snapshot of everything you've done, because otherwise if the server, in some classes previous, the server has crashed and students have lost their work. But yeah, so that's one of the things. And then the reason why you're putting all that in is then at the end, you'll be able to generate a report, and this will generate a Word document, which I will show you quickly here. Is that it will generate a document where it'll have some information in and around this class, and all your answers that you have input in will be going into, will be populated in here. So there are buttons on here to navigate through, and then we're going to kind of work through up until activity A, and then we're going to bring everyone back in. But yeah. So does anybody have any questions before we head out into the breakout rooms?
So the file should be open like with Internet Explorer, or with when you load your user inputs, how, yeah, this file should be open.
Which file, sorry?
When you do the load user input, so.
Oh yeah, so yeah, good. Yeah, so when you download that file, what you do,
yeah.
If you have to reload it, you can go back to the introduction tab.
Yeah.
And there's a place here to browse, and you can upload. You can upload that file, and it will put your answers back in. So you just select it and open it, and then it will upload it, and then you'll see it'll have filled in some of the answers. Thanks, Anna.
Okay.
Okay.
Is anyone having any trouble accessing the site? Because I've got the breakout rooms all queued up. And the way that I've divided it just very randomly is with the title of the breakout room is associated with one of the lakes for that you'll be generating a forecast for, just so that we have a diversity of lakes for discussion at the end.
Okay, so
Ready?
Oh, sorry.
I'm adding in the keep going.
Oh yeah, I was just gonna say, if everyone could, if you have the app open, you could use the thumbs up reaction in Zoom, just so we can see if anyone's having any issues. Okay. I think we're good to go to.
And then Tadhg will bring them back after activity A-ish, and Ryan and Tadhg and I will kind of zoom around.
Yeah, so if you have any further questions, we'll be around to the breakout room.
I wasn't placed in one.
No,
Maybe
I
as I'm a
didn't.
co-host.
I was gonna put you in. I was gonna wait. I'm gonna put you into Prairie Lake. Whoops. Actually, do you mind being able to jump in yourself? Is that okay?
Sure. Prairie Lake. Okay.
Do you have it? Okay. I just moved you. Is that good? Stop recording. We're good.
Oh yeah.